Hello students, in this unit we will discuss summation of series. First of all, we discuss some basic terminology associated with the series. In a series, we are working with the sum of terms of a sequence. A series may be either finite or infinite. A finite series is a series that has a sum of a finite number of terms. An infinite series is a series that has a sum of an infinite number of terms. The capital Greek letter sigma is used to indicate a summation. Summation notation is a shortened way of representing the sum of certain terms of a sequence. If the difference between successive terms of a series is a constant, then the series is said to be an arithmetic series. A series for which the ratio of each two consecutive terms an plus 1 by an is a constant function of the summation index n is called a geometric series. Sequences and series. A sequence is a list of numbers. The order in which the numbers are listed is important. So, for example, 1, 2, 3, 4, 5 dash dash is one sequence and 2, 1, 4, 3, 6, 5 dash dash is an entirely different sequence. A series is a sum of numbers. For example, 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 plus dash dash is an example of a series. A series is composed of a sequence of terms that are added up. Sequences and series are often confused because they are closely related to each other. But when we say sequence, we are not concerned with some of the values of the terms, whereas in a series we are interested in such a sum. For example, 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6 dash dash is a sequence, and it is obvious that the nth term will be 1 by n. Clearly, as n tends to infinity, the limit of the sequence is equal to 0. In general, if a1, a2, a3 dash dash an is a sequence, and then the expression a1 plus a2 plus a3 plus dash dash plus an is called a series. If the sequence is finite, the corresponding series is a finite series. If the sequence is infinite, the corresponding series is an infinite series. Example, 1, 2, 4, 8, 16 is a finite sequence. 1 plus 2 plus 4 plus 8 plus 16 is a finite series. Summation. Summation is the operation of adding a sequence of numbers. The result is their sum or total. The capital Greek letter sigma is used to indicate a summation. Example, for the summation of the sequence of consecutive integers from 1 to 100, one could use an addition expression involving ellipses to indicate the missing terms as follows: 1 plus 2 plus 3 plus dash dash plus 99 plus 100. In this case, the reader easily guesses the missing integers. Series are often represented in a compact form called summation notation, which is the stylized version of the capital Greek letter sigma. Using this notation, the above summation is written as sigma k is equal to 1 to 100 k. The value of this summation is 5050. It can be found without performing 99 additions as follows: sigma k is equal to 1 to 100, k is equal to k into k plus 1 by 2, which is equal to 100 into 100 plus 1 by 2, which is equal to 5050. Example 1. Sigma k is equal to 1 to 4, ak is equal to a1 plus a2 plus a3 plus a4. Sigma k is equal to 0 to n, xk is equal to x0 plus x1 plus x2 plus dash dash plus xn. Sigma k is equal to 1 to n, 1 by 2 raised to k is equal to 1 by 2 plus 1 by 4 plus 1 by 8 plus dash dash plus 1 by 2 raised to n. Properties of finite series. The following are the properties for addition or subtraction and scalar multiplication of series. These properties will help to calculate series whose general term is a polynomial. Sigma I is equal to m to n ai plus or minus bi is equal to sigma I is equal to m to n ai plus or minus sigma I is equal to m to n bi. Sigma I is equal to m to n cai is equal to c into sigma I is equal to m to n ai. Theorems of finite series. The following theorems give formulae to calculate series with common general terms. These formulae, along with the properties listed above, make it possible to solve any series with a polynomial general terms as long as each individual term has a degree of 3 or less. Sigma I is equal to 1 to n, 1 is equal to n. Sigma I is equal to 1 to n, c is equal to nc. Sigma I is equal to 1 to n, I is equal to n into n plus 1 by 2. Sigma I is equal to 1 to n, I square is equal to n into n plus 1 into 2n plus 1 by 6. Sigma I is equal to 1 to n, I cube is equal to n into n plus 1 by 2 the whole square. Telescopic series. If the terms of the series are alternately positive and negative, it is called a telescopic series or alternating series. Example, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 minus 1 by 6 is a finite telescopic series. It can be symbolically represented as sigma k is equal to 1 to 6 minus 1 all to the power of k minus 1 by k. In general, sigma n is equal to 1 to infinity bn minus bn plus 1 is an infinite telescopic series. Problems. 1. Write the following series without summation notation. 1. Sigma k is equal to 1 to 5 k minus 1 by k. 2. Sigma k is equal to 0 to 5 minus 1 all to the power of k by 2k plus 1. Solution. 1. Sigma k is equal to 1 to 5 k minus 1 by k is equal to 1 minus 1 by 1 plus 2 minus 1 by 2 plus 3 minus 1 by 3 plus 4 minus 1 by 4 plus 5 minus 1 by 5 is equal to 0 plus 1 by 2 plus 2 by 3 plus 3 by 4 plus 4 by 5 is equal to 1 by 2 plus 2 by 3 plus 3 by 4 plus 4 by 5. 2. Sigma k is equal to 0 to 5 minus 1 all to the power of k divided by 2k plus 1 is equal to minus 1 to the power of 0 divided by 2 into 0 plus 1 plus minus 1 all to the power of 1 by 2 into 1 plus 1 plus minus 1 all square divided by 2 into 2 plus 1 plus minus 1 all cube by 2 into 3 plus 1 plus minus 1 all raised to 4 by 2 into 4 plus 1 plus minus 1 all raised to 5 divided by 2 into 5 plus 1 is equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus 1 by 9 minus 1 by 11. 2. Write the following series using summation notation. 1. 1 minus 2 by 3 plus 4 by 9 minus 8 by 27 plus 16 by 81. 2. 1 square plus 2 square plus 3 square plus dash dash 6 square. 3. 1 plus 1 by 2 square plus 1 by 3 square plus dash dash 1 by n square. Solution. Start with k is equal to 0. Sigma k is equal to 0 to 5 minus 1 all to the power of k into 2 by 3 all raised to k. Start with k is equal to 1. Sigma k is equal to 1 to 5 minus 1 all to the power of k minus 1 into 2 by 3 all raised to k minus 1. 2. Sigma k is equal to 1 to 6 k square. 3. Sigma k is equal to 1 to n 1 by k square. Proving a summation formula. Example. Prove that for all positive integers n, 1 by 2 plus 1 by 4 plus 1 by 8 plus dash dash 1 by 2 raised to n is equal to 2 raised to n minus 1 by 2 raised to n. Proof. First of all, we use the conjecture as Pn such that 1 by 2 plus 1 by 4 plus 1 by 8 plus dash dash plus 1 by 2 raised to n is equal to 2 raised to n minus 1 by 2 raised to n. Now we use the principle of mathematical induction to prove the same. To show that P1 is true, P1 is equal to 1 by 2, which is equal to 2 raised to 1 minus 1 by 2 raised to 1. Thus P1 is true. Now we assume that Pk is true. Then we have to show that Pk plus 1 is also true. We have Pk is equal to 1 by 2 plus 1 by 4 plus 1 by 8 plus dash dash 1 plus 1 by 2 raised to n is equal to 2 raised to k minus 1 by 2 raised to k. Now we show that Pk plus 1 follows from Pk. We start with the true statement pk and add 1 by 2 raised to k plus 1 to both sides, and simplifying the right side we get 1 by 2 plus 1 by 4 plus 1 by 8 plus dash dash plus 1 by 2 raised to k plus 1 by 2 raised to k plus 1 is equal to 2 raised to k minus 1 by 2 raised to k plus 1 by 2 raised to k plus 1 is equal to 2 raised to k minus 1 divided by 2 raised to k into 2 by 2 plus 1 by 2 raised to k plus 1 is equal to 2 raised to k plus 1 minus 2 plus 1 divided by 2 raised to k plus 1 is equal to 2 raised to k plus 1 minus 1 divided by 2 raised to k plus 1. Now we have proved that if pk is true, then pk plus 1 is also true. Therefore, by the principle of mathematical induction, the result is true for all positive integers n. An arithmetic series is the sum of a sequence, the set ak, k is equal to 1, 2, 3 dash dash, in which each term is computed from the previous one by adding or subtracting a constant d. Therefore, for k greater than 1, ak is equal to a into k minus 1 plus d, which is equal to a into k minus 2 plus 2d is equal to dash dash is equal to a1 plus d into k minus 1. Some formula for a finite arithmetic series. If a1, a2, a3 dash dash an is a finite arithmetic sequence, then the corresponding series a1 plus a2 plus a3 plus dash dash plus an is called an arithmetic series. Let d be the common difference of the arithmetic sequence a1, a2, a3 etc. an, and let Sn denote the sum of the series a1 plus a2 plus a3 plus dash dash plus an. Then Sn is equal to a1 plus d plus a1 plus 2d plus dash dash a1 plus n minus 2 into d plus a1 plus n minus 1 into d. Let it be equation 1. Reversing the order of the sum, we get Sn is equal to a1 plus n minus 1 into d plus a1 plus n minus 2 into d plus dash dash plus a1 plus 2d plus a1 plus d plus a1. Adding LHS and RHS of equations 1 and 2, we get 2Sn is equal to 2a1 plus n minus 1 into d plus 2a1 plus n minus 1 into d plus dash dash plus 2a1 plus n minus 1 into d, which is equal to n into 2a1 plus n minus 1 into d. Therefore, Sn is equal to n by 2 into 2a1 plus n minus 1 into d. By rearranging a1 plus n minus 1 into d with an, we get Sn is equal to n by 2 into a1 plus an. Some formula for a finite geometric series. A geometric series sigma k is equal to 1 to n ak is a series for which the ratio of each two consecutive terms ak plus 1 by ak is a constant function of the summation index k. Let R be the common ratio of the geometric sequence a1, a2, a3 etc. an, and let Sn be the sum of the series a1 plus a2 plus a3 plus dash dash plus an. Then Sn is equal to a1 plus a1r plus a1r square plus a1r cube plus dash dash plus a1r raised to n minus 2 plus a1r raised to n minus 1. Let it be equation 1. Multiplying both sides of this equation, we get Rsn is equal to a1r plus a1r square plus a1r cube plus dash dash plus a1r raised to n minus 1 plus a1r raised to n. Let it be equation 2. Then 1 minus 2 implies Sn minus Sn minus 1 is equal to a1 minus a1 into r raised to n. That is, Sn into 1 minus r is equal to a1 into 1 minus r raised to n. Therefore, Sn is equal to a1 into 1 minus r raised to n divided by 1 minus r not equal to 1, or Sn is equal to a1 minus r an divided by 1 minus r not equal to 1. Therefore, an is equal to a1 r raised to n minus 1. Letting modulus of r less than 1, say r is equal to 0.5, we can quickly see how this sequence behaves by modeling it using a spreadsheet as follows. What will happen if r had been greater than 1? Let r is equal to 2 and repeat the modeling. The first 10 terms of this sequence with the graph is given below. Sum of an infinite geometric series. S infinity is equal to a by 1 minus r. modulus of r less than 1. If modulus of r greater than or equal to 1, then the infinite geometric series has no sum. Problems. Evaluate the sum sigma k is equal to 1 to 5 3 raised to k. Solution. Sigma k is equal to 1 to 5 3 raised to k is equal to 3 raised to 1 plus 3 raised to 2 plus 3 raised to 3 plus 3 raised to 4 plus 3 raised to 5. This is a geometric series with a common ratio of 3. Here n is equal to 5, a1 is equal to 3, r is equal to 3. Therefore, s5 is equal to 3 into 1 minus 3 raised to 5 by 1 minus 3, which is equal to minus 726 divided by minus 2 is equal to 363. Problem 2. Find the sum of the first 10 terms of the geometric sequence minus 5, 15, minus 45, 135, dash dash. Solution. We have Sn is equal to a1 into 1 minus r raised to n, all divided by 1 minus r not equal to 1. Here n is equal to 8, a1 is equal to minus 5 and r is equal to minus 3. Therefore, S10 is equal to minus 5 into 1 minus minus 3 all raised to 10 all divided by 1 minus minus 3, which is equal to minus 5 into 1 minus 59,049 divided by 4 is equal to 59,039 divided by 4 is equal to 14,759.75. Problem number 3. Find S6 for the sequence an is equal to 3 into 4 raised to n minus 1. Solution. By comparing that to the formula given in this problem, we find a1 is equal to 3 and r is equal to 4. Substituting these values into the equation, Sn is equal to a1 into 1 minus r raised to n by 1 minus r. Therefore, S6 is equal to 3 into 1 minus 4 raised to 6 divided by 1 minus 4 is equal to 3 into 1 minus 4096 by minus 3 is equal to 3 into minus 4095 by minus 3 is equal to 3 into 1365 is equal to 4095. Problem 4. Solve the series sigma n is equal to 1 to 20 2n square plus 7n. Sigma n is equal to 1 to 20 2n square plus 7n is equal to sigma n is equal to 20 2n square plus sigma n is equal to 1 to 20 7n is equal to 2 times sigma n is equal to 1 to 20 n square plus 7 times sigma n is equal to 1 to 20 n is equal to 2 into 20 into 20 plus 1 into 2 into 20 plus 1 all divided by 6 plus 7 into 20 plus 1 by 2 is equal to 2 into 17,220 by 6 plus 7 into 420 by 2 is equal to 17,220 by 3 plus 7 into 210 is equal to 5,740 plus 1,470 is equal to 7,210. Therefore, sigma n is equal to 1 to 20 2n square plus 7n is equal to 7,210. Harmonic sequence. Harmonic sequence is the reciprocal of an arithmetic sequence. For example, the sequence 2, 4, 6, 8 is an arithmetic sequence. Then the corresponding harmonic sequence is 1 by 2, 1 by 4, 1 by 6, 1 by 8. That is, the sequence A1, A2, A3, etc. is said to be in harmonic if their reciprocals 1 by A1, 1 by A2, 1 by A3, etc. are in arithmetic sequence. Harmonic series. The series sigma n is equal to 1 to 5, 1 by k is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 is an example of a finite harmonic series. The series sigma k is equal to 1 to infinity 1 by k is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus dash dash is an example of an infinite harmonic series. An harmonic series is just the sum of a harmonic sequence. No harmonic series converge. The following figure depicts the first 20 terms of the harmonic series based on 1 by n and its graph. Alternating harmonic series. The series sigma n is equal to 1 to infinity minus 1 all to the power of n plus 1 by n is equal to 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 minus dash dash is known as the alternating harmonic series. In particular, the sum is equal to the natural logarithm of 2 that is 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 minus dash dash is equal to natural logarithm of 2. Here are some problems for you to solve. Problem number 1. Write the series sigma k is equal to 1 to n 1 by 2 raised to k without summation notation. Problem number 2. Write the series 1 minus 4 plus 9 minus dash dash plus minus 1 all to the power of n plus 1 into n square using summation notation. Problem number 3. Evaluate sigma I is equal to 1 to 6 for I square minus 5. Problem number 4. What is the sum of the infinite series 2 plus 1 plus 1 by 2 plus 1 by 4 plus dash dash up to infinity? Problem number 5. Find the nth term of the arithmetic sequence minus 2, minus 8, minus 14, minus 20 dash dash. Sixth one. Find the 31st term of an arithmetic progression whose 11th term is 38 and the 16th term is 73. Seventh one. Find the sum of the geometric series 18 plus 6 plus 2 plus dash dash. Books for reference. Advanced Engineering Mathematics by Peyton V. O. Neal. Introduction to Calculus and Analysis by Richard Fritz John. Thank you all. See you next time.